Good morning, everyone. This is Ekta, student of 5-year integrated Maths Honors 5.6, roll number 5329. The topic of my presentation is Connectedness in Topology. Before discussing the definition of connectedness, we should define what are separated sets. So let's define. Let E be any subset of a topological space Xt, then two subsets A and B of E are said to form a separation or partition of set E in topological space Xt, which can be written as E is equal to A upon B if and only if it satisfies the following condition. First one, E is equal to A union B, that is, E can be expressed as the union of two subsets A and B, where A and B are non-empty sets and A intersection B is equal to phi, that is, A and B are disjoint sets. Second property, closure of A intersection B is equal to phi and A intersection closure of B is equal to phi, that is, neither A contains a limit point of B and nor B contains a limit point of A. Now let's discuss an alternative definitions of separated sets. The two sets A and B are said to be separated if closure of A intersection B union A intersection closure of B is equal to phi. If this condition is satisfied, then we can say that the sets A and B are separated sets. Now let's come to the definition of connected set. A subset E is said to be connected in topological space Xt if it has no separation of E. That is, a set is a connected set if it is not a separated set. That is, if E can be expressed as the union of A and B, where A and B are non-empty subsets, then either A intersection closure of B must not be equal to phi, or the closure of A intersection B must not be equal to phi. Then the set is called a connected set. Now let's discuss some examples of connected set. An empty set is connected set. How? As we know that phi, which is an empty set, cannot be expressed as the union of any two non-empty sets, and hence we can say that empty set is a connected set. Now the next example is that every singleton set is connected set. As small x belongs to x, the closure of x intersection x, and as closure of x can be expressed as x union derived set of x intersection x. As we can see that x singleton x is common in this, so as the answer is singleton x, which is not equal to phi, and hence we can say that every singleton set is a connected set. Example 3. The interval A is equal to open interval 1, 2 and B is equal to closed 2, 3 open are connected. As we know that closure of A is equal to close interval 1, 2 and closure of B is equal to close interval 2, 3. So the closure of A intersection B is 2, which is not equal to 5, and A intersection closure of B is equal to 5. Therefore, we can say that A and B are connected sets. Now, let's discuss some theorems. Theorem number 1. Let X star and Y star be a subspace of topological space Xt and E be a subset of X star. Then C star E is equal to X star intersection CE, where CE is the closure of E in T and C star E is the closure of E in T star. This theorem is very important as it is used in further theorems and examples. Theorem 2. Let X star and Y star be a subspace of a topological space Xt and E is a subset of X star. Then E is T star connected if and only if E is T connected. Let E is equal to A union B. That is, E can be expressed as the union of any two non-empty sets and AB belongs to T star. So now we find C star A intersection B union A intersection C star B. From the result of theorem 1, that is, we can write C star E as X star intersection CE. Similarly, we can write in place of C star A X star intersection CA and intersection B as it is union A intersection. Similarly, in place of C star B, we can write X star intersection CB. Now, rearranging the terms, we write CA in the front and intersection X star intersection B together. Union the term as it is. Now, as we know that B is a subset of X star and A is a subset of X star, so X star intersection B is equal to B and A intersection X star is equal to A. So CA intersection B intersection A intersection CB, where C star A and CA are closures of A with respect to the topologies T star and T respectively. Now E is T star connected. So the left hand side, this C star A intersection B union A intersection C star B is not equal to phi, because as we have discussed in the alternative definition of separated sets, two sets are said to be separated if CA intersection B union A intersection CB is equal to phi. And from this definition, if we want to define connected sets, then we can say that closure of A intersection B union A intersection closure of B is not equal to phi. So we write here this is not equal to phi, and as this is equal to closure of A intersection B union A intersection closure of B, so it is also equal to phi, and hence from this we can say that E is T connected. Now let's move on to the next theorem. Theorem 3. If C is a connected subset of a separated topological space Xt with X is equal to A upon B, then either C is a subset of A or C is a subset of B. Let's prove it. Since it is given that X is equal to A upon B, that is, X can be expressed as the union of any two non-empty subsets A and B, where A and B are disjoint sets, and from the second condition of separated sets, closure of A intersection B is equal to phi, and A intersection closure B is equal to phi. Now we can write C is equal to C intersection X because C is a subset of X. So intersection of C with X is equal to C only. We can write as X is equal to A union B, so we can write A union B in place of X. So the equation becomes this. Now we apply the distributive property and obtain this C intersection A union C intersection B, where C intersection A and C closure of C intersection B is a subset of A intersection closure C closure A intersection closure B is equal to phi, because the intersection of C and A is A and the intersection of C and B is B. Similarly, we can write closure of C intersection A intersection C intersection B is a subset of closure of A intersection B, which is equal to phi. If C intersection A is not equal to phi and C intersection B is not equal to phi, then these two sets form a separation for C, right? Then these two sets form a separation for C, but it is given in the theorem that C is connected. Therefore, either C intersection A is equal to phi or C intersection B is equal to phi. That is, C is a subset of A or C is a subset of B. Hence, proved. Now, here are some online references. So you can go through these to know more about connectedness in topology, and here I have mentioned some book references for deep knowledge of this content. Thank you.